Hello everyone, I'm Zechun from Xi'an Jiaotong University, China. Happy to be here to present our work, NDD, a design diagram for network verification. This is a joint work with Peng Zhang, Yichi Zhang, and Hongkun Yang. Computer networks are complex and prone to misconfigurations, which can lead to global service outages and financial losses. In recent years, researchers have put a lot of effort in the network verification, which use formal methods to check the correctness of network configurations and can prevent the network outages. A key idea in the network verification is equivalence class over a network state. For data plan verification, if two packets are forwarded to the same port on each device in the network, then those two packets belong to the same equivalence class. For example, based on the match condition of the forwarding rules here, the veriflow will partition the header space into 5 equivalence classes using a multi-dimensional trie. And the classes of 1 and 5 can only match the rule C, and the classes of 2 and 4 can match the rules of B and C, and class 3 can match all the rules. By just checking the behaviors of a small number of equivalence classes, verification tools can greatly reduce the verification space. However, as we can see here, two equivalence classes 1 and 5 actually encode the same forwarding behavior, but they belong to non-adjacent ranges, and we cannot merge them by using the multi-dimensional trie. Binary decision diagram, or BDD, can encode multiple ranges by a single Boolean formula and represent the formula as a graph. And as we can see here, it's more compact than the multi-dimensional trie used by veriflow. And BDD is a rooted directed cyclic graph with 2 terminal nodes, true and false, and multiple non-terminal nodes. Each non-terminal node encodes a Boolean formula and have 2 edges. The dashed edge represents that assign 0 to the variable, and the solid edge represents assign 1 to the variable. And each path in the graph represents a truth assignment. And for example, the red path here represents that the variable A equal to 0 and B equal to 1. Compared with the binary decision tree, the binary decision diagram can merge equivalent nodes with the same variable and edges, and can remove the redundant nodes with two edges pointing to the same descendant, and therefore achieve a better performance. BDD has been widely used in the symbolic model checking, and for network verification, many verifiers today use BDD to achieve a more compact representation of the equivalence classes. Although BDD has been widely used, however, we find that when used for network verification, BDDs show 3 major limitations. To better show the 3 limitations, we use a simple example here with 4 devices, and we suppose that the field of source IP has only 4 bits, and the other fields each has only 2 bits. And on each device, there are forwarding rules match the destination IP field, and ACL rules filtering packets according to the 5 tuple. For example, on the device A, the first forwarding rule states that only the packets with destination IP equal to 00 will be forwarded to the port 1, and the ACL rules states that only the packets with the destination port equal to 00 will be allowed by the port 1. And now let's see the limitations of BDD. The first limitation is redundant nodes. As for the packets that can reach the device D from the device A, the BDD on the right encodes all the packets that can follow the path of ACD. And for the other 2 passes of AD and ABD, we have another 2 BDDs encode the corresponding packets respectively. And we can see that these 3 BDDs share a same structure in the field of source IP and source port. However, because they have the different structures in the field of destination IP and port, the same structures are created 3 times, and we cannot reduce such a redundant node in BDD. And the second limitation is deep recursions. Suppose now we need to compute the conjunction of the node A1 and B3 to perform the logical operation. BDD first need to align the variables. That means one needs to traverse from the node A1 with multiple recursions, and each recursion looking at a single bit until it reaches the node B1, which encodes the same variable as B3. Only from this point, the effective part of the operation can start. And it's clear that such a bit-by-bit traversal wastes time because the packet header often has tens of bits. And the last limitation is due to the explosion of atoms or equivalence classes. To show this, we simplify the example by removing the ACL rules on device D. And if we suppose there are only ACL rules, we will get 3 different behaviors in the destination port. And similarly, if there are only forwarding rules, we will get 3 different behaviors. But we can see that BDD-based verifiers compute atoms according to all the fields simultaneously, and we will get 3 times 3 equals to 9 atoms in total, which are actually the cross product of the behaviors in different fields. And so why NDD has about limitations when used for network verification? We observe that this is mainly due to the different semantics of BDD and network forwarding. BDD makes decisions at the level of bit, but the network makes decisions at the level of field, which often has tens of bits. And we propose a new decision diagram for network verification, that is network decision diagram, or NDD. Next, I will show what the NDD is and how NDD overcomes the limitations of BDD. The first idea of NDD is to partition the whole network state into a set of fields and declare a separate namespace for each field. To be more concrete, NDD will create per field BDDs into the corresponding namespace such that the logical operations are restricted to the BDD in the same namespace. And in the example, we have 4 fields and 4 namespaces. And we can see that the redundant nodes in the field of source IP and source port are reduced because each value is only encoded once in the corresponding namespace. And after decoupling the fields, NDD can reduce its redundant nodes. And now the problem is how to represent the multi-field network states with these per-field BDDs. To solve the problem, we use another layer of design diagram to assemble the per-field BDDs, and we call such a design diagram as NDD. And different from BDD, each NDD node has multiple edges and encode an entire field. And each edge is labeled with BDD, representing the value that can take on the field. And now return to our previous example. If we want to compute the conjunction of A1 and N3, using NDD, the logical operation still needs multiple recursions to align the variable, but each recursion now looking at an entire bit, and therefore such the process is much faster than that of using BDD. And since NDD has decoupled the fields, it can compute atoms for each single field. And we can see here in our example, when using BDD, we get 3 times 3 equals to 9 atoms, but using NDD, we get only 3 plus 3 equals to 6 atoms. And that shows the NDD can overcome the explosion of atoms. And also, by replacing the label on the edge, which is a BDD, with a set of equivalent atoms, NDD can further speed up its logical operation. Recall that the BDD achieve a compact representation of Boolean formula according to these 2 reduction rules. And for NDD, we have a similar form of these 2 reduction rules. First, if 2 NDD nodes has the same variable and edges, we will merge these 2 nodes into a single one without affecting the Boolean formula. And second, if NDD node has only one edge, labeled with the BDD true, then we will remove this NDD node since it's redundant. And in addition to these two reduction rules, we have a third rule that is unique to NDD. That is, if two edges of the same NDD nodes point to the same descendant, we will merge these two edges into a single one, and the BD label on the new edge is a disjunction of the two BD labels on the old edges. In our paper, we prove that by applying these three reduction rules, the NDD satisfies the property of canonicity. That means for any Boolean function, if the ordering of the variables is fixed, there is exactly one NDD node that can represent the function. And when designing the NDD, we are faced with several challenges. One challenge is how to reduce the memory overhead of each NDD node, since each NDD node can have multiple edges, and with each edge labeled by a BDD. To solve the problem, we eliminate all the edges point to the terminal false. And for more challenges and solutions, please refer to our paper. And we implemented our NDD libraries based on two BDD library, JDD and Java BDD respectively, and we made them open source on our website. Using our NDD library, we implemented 5 BDD-based verifiers, including AP verifier, APT, APKeep, SRE, and batfish, with minor modifications to their original source code. And now we evaluate the NDD performance when used for network verification. First, we run Katra and APKeep on a VXLAN-based virtualized data center network, which are synthesized according to production networks. Then we run the NDD-based APKeep on the same data site to check the pairwise reachability, and we can see that the result shows NDD-based APKeep runs 5 orders of magnitude faster than its BDD version, and even order of magnitude than Katra. And such speed up is mainly due to much less atoms or equivalence classes. And we can see in the table, NDD-based APKeep compute much less atoms by computing atoms for each single field compared to its BDD version. And the Katra and APKeep are data plan verifiers. So how about the control plan verifiers? To answer this question, we run the control plan verifiers based on BDD, batfish, and SRE on the different sizes of fat tree networks running BGP. And we also run their NDD version. And the result shows that by replacing BDD with NDD, SRE runs 2 orders of magnitude faster than its BDD version. And as for batfish, since it's only encode a single destination IP in this data site, the improvement is not quite significant. And an interesting point I want to share is NDD is actually not limited to the field of network verification. For example, NQueen's problem has been used as benchmark to test the performance of different BDD libraries. And we also solve this problem with our NDD library. And the result shows that when solving the problem with a larger N, using NDD is faster than using BDD. For example, when the N equals to 12, the BDD takes 19 seconds and NDD only takes 12 seconds. And that means NDD may be applied to a broader range of scenarios beyond the network verification. And to conclude, we found that although BDD is very efficient, but when used for network verification, it has limitations of redundant nodes, deep recursions, and explosion of atoms. And we propose the network design diagram, which is customized for network verification and can solve these problems. And we show that NDD performs better in data plan and control plan verification. And for more experiments, please refer to our paper. And with that, I'm happy to take any questions. Thank you.